Good morning, everyone. So last class, we finished the completely randomized design code. And today, my goal is to have a brief lecture on RCBD, just so we kind of remind ourselves of the differences there, especially when we choose RCBD over CRD. And then we're going to be talking about the model, how the model changes, how the ANOVA table changes, and then we're going to get into an exercise, or actually a couple of exercises. So I noticed after we were done with the CRD exercise that I meant to show you all how to do treatment randomization in R for a study. We're going to go again through the example of what we're doing here, but my goal is that you understand how you would do this in R and how you could do this for your own studies, which I know the growing season here, if you have, field crop research, growing season is coming up. So perhaps you are getting ready to randomize your trials. So I do want to go through that first. So we're going to see how we would randomize in R and how to create a plot layout for a CRD study and also an RCBD study. And then we're going to get into the RCBD analysis part of the exercise. With that, let's get started with the randomized complete block design lecture. So again, I just posted this morning that to the website. So it's going to be this lecture here under February 8th. So if you click on that link, that's going to take you to those sets of slides. So you know that already that you can download these HTML slides as PDF in case you want to take notes on them. And also if you want to just follow along with me here or even after directly on the website, you have a link for it. All right, so today, this quick lecture here on randomized complete block design. So the goals of these slides here, this presentation, is to talk about some of these concepts that we relate to randomized complete block designs. So the case here would be heterogeneous experimental material. How is randomization different? Because it will be different than a CRD. So how different is that? Let's take a look at the effects model as well to understand, and this is going to be key because again, you can plan your study, you can randomize properly in the field, collect your data. But when it comes time for you to specify your model to your software, if you don't know how to properly specify that model, you may specify the wrong model. R, SAS, Python, whatever it is not going to know that you're specifying the wrong model. So it's important to know what model you should specify to make sure that you complete that cycle of planning, implementing, and analyzing properly this study. And then we're going to see how that effects model translates into the ANOVA table. There's going to be a few differences there as well for us to notice. Okay, so our motivational example, we're just going to refresh our minds here. So we've been talking about a two-way factorial where we have, the first factor is nitrogen fertilizer rates. We have 0, 100, and 200 kilograms of nitrogen per hectare as the levels. The second factor is potassium fertilizer rates, where we have 0, 30, and 60 kilograms of potassium per hectare as the levels. And we are doing a full factorial, meaning that we have all combinations. So we have 9 treatment combinations in this study. And if we assume that we have heterogeneous experimental material, so in this case would be different soil type, topography, it could be anything, any other factor here. Those are normally the two most common, I guess, but it could be other things as well. That would be affecting the heterogeneity or homogeneity of your experimental material would be something that you consider here. So if we assume that, we should use a randomized complete block design to account for that source of heterogeneity, especially to include that with the block effect. Now, because we are using, so now, we refer to a replicate in more general terms. When it comes to a randomized complete block design, a replicate is the equivalent of a block, right? So in this case here, we're going to be randomizing our treatments to our plots or experimental units in a restricted way. Remember that CRD was unrestricted. We had no restrictions on how we were randomizing. In a randomized complete block design, it has one factor of restriction, that is the block. So in that case, we do want that for each treatment to appear once in each block. And because of that, we need to randomize those treatments individually for each one of those blocks. So now instead of having all 36 possible treatment combinations and their replications in a hat, and you're just drawing each one and just going through your plot number sequentially, now we're going to have basically 9 pieces of paper where each one of them have one treatment once. And then we're going to say, okay, block 1, the first plot of that block, I'm going to randomly assign a treatment, and then do the same for the second plot and so on. When you finish block 1, you basically put all the papers back in the hat, reshuffle them, and do the same process for block 2, then block 3, then block 4. So we are randomizing the treatments to the plots individually at the block level. So in our motivation example, we have 4 replicates, so we have a total of 36 experimental units. And in this case here, the 4 here is our number of reps. Remember that for the CRD, these reps were just like, it was just multiplying the treatments by the reps. That's total plots that we have, and a treatment could fall in any of those plots. And in this case here on the CRD, we're going to have this restriction that is going to be the block effect. So this is just that example of, in this case here, if we're assuming that we have 2 different soil types, we need our blocks to be completely confined within a given soil type, because then that effect of soil type is going to be attached to the block. And because we have blocks, then we can include that blocking term in the model, and it will kind of suck up that variability coming from soils to the block effects. So that's going to decrease that variability that would be otherwise appearing on the treatment effects, and is going to allow us still to be able to make fair and unbiased treatment comparisons, even if you have different soil types in this case. So I'm just highlighting here treatment number 1 differently. So if you remember this plot here when I was showing the CRD, if you recall, the CRD was just one soil type in the background, so it's just the dark soil type here. And we were randomizing without restriction. That meant that treatment 1 actually fell twice in the first column, and it was not present in the third column at all. It was in the first and fourth as well. So in this case here, each treatment, in this case, highlighting treatment 1, is going to appear once in every block because we're randomizing that way with the block restriction. Yes, that's just basically what I said. And since we do have heterogeneous experimental material and we are using blocks, we are safeguarding the power of this analysis by using blocks, right? So, there's a few scenarios here that you can imagine where one is, if your field is completely homogeneous, you should use CRD. However, if you do choose to have a homogeneous field and still use RCBD, it's not going to greatly hurt you. It's going to hurt you a little bit, and we're going to see that when we get to the ANOVA table. But the worst that it could be is you have heterogeneous material and you use CRD, because now you don't have a term in your model that can suck up that external variability source and still leave your treatments unbiased and fairly comparable. If you do have heterogeneous material and you use a CRD. So if your field is homogeneous, the best to use a CRD. If your field is homogeneous and you use RCBD, okay, it's not hurting yourself that much. A little bit, we're going to see that again in the ANOVA table, but the worst case is you have heterogeneous field and you use a CRD. Then you just really cannot fairly remove that effect of soil on your model. So in this case, we're just seeing an example where field is heterogeneous, we're using RCBD, so we're doing the correct thing. Okay, let's take a look at the effects model. There is one little difference here between the effects model of the RCBD for our two-way factorial example and the CRD. That difference is basically just this PK term that now is present here. So before we did not have this PK, and that was the model for CRD. Now we do have this PK term here that basically relates to the differential effect of the kth block. So now we have a block term in our model. And remember that what you have in your model is going to be represented in your ANOVA table. So we're going to also have a line in our ANOVA table for the block effects. And everything else is the same. So the alpha i's is the differential effect of the ith nitrogen rate. The betas are for the potassium rate. The alpha beta coefficients are for that interaction between nitrogen and potassium. And lastly, we have our residual or error term that is just what's left over from what we observe and all these terms in the model. Yeah.
So I have a question about this model. So when we will define our like all the factors that we have used, so this model will be defined by our ANOVA table, or we will get this model from some kind of software, or
So,
how we will generate it?
okay, I think there's a couple of ways I can answer that, and I'm gonna go one way, and if it doesn't answer what you're asking, then we can try again. So this model is what is actually gonna be run behind the scenes, right? What happens is when you come in R and you specify your model, we don't have to specify the overall mean. That's implied in the model syntax. So if you remember in R, we were using the function LM, right? So LM and then EO tilde and then all the factors. So all these factors here, even though we're not gonna call them alpha, beta and EIJ, we're gonna call them, so it's gonna be yield equals to, we do not specify the overall mean. We will, in this case, specify the block effect. So that is gonna come up on the exercise of RCBD when we go through it. And then we will specify nitrogen rate, potassium rates, and the interaction. So that model, that's the level, the LM function in this case, that's the level where you do specify this model. However, you only see the ANOVA table after you run the ANOVA function, right? So the model is set up here, and then we have to look at the ANOVA table results based on this model using a different function. That's the ANOVA function, right? So really, if you think about it, this is what we would call analysis of variances at this level, right? This is analysis of variance right here. And then you do that on the LM function. And then when you do want to look at the ANOVA table based on this ANOVA model, that's when you would call the ANOVA function. So the ANOVA function is not running a model for you, it's just putting this in terms of the ANOVA table columns, right? So the source of variation, which are related to the effects, sum of squares, mean squares, F ratio, p-value.
So these symbols that they use here, like that mu, that is standardized, and EIJK, that is also standardized. But in most of the papers, they will sometimes use, instead of A and B, they will use some other symbols. So that these are not standardized. We can adjust them according to our requirements or according to what we like, right?
Yeah, so I guess like if you do go by textbook notation, there is going to be a somewhat standard notation. But yeah, especially, I mean, the YIJK and the EIJK are perhaps the most, as you said, the most common to see that way. But when it comes to the actual terms of your model, the block, I guess, can be something else. Like you could call that B if that makes sense, So yeah, but I agree with you that, you could follow a standardization that there is in the literature, but it's not like if you don't follow that, somebody's going to complain at you. Yeah, great. Any other questions, I guess, at this point? All right, so I do want to remember just for the next 10 seconds, this model here. So we have an overall mean, we have the block effect, and then the main effect of nitrogen, potassium, their interaction, and the error, the residual. Now let's take a look at how that translates to the ANOVA table. And just as a reminder, N is the number of levels in nitrogen rate, so that's equal to 3. K is the levels of potassium, so that's 3. R is number of blocks, in this case 4. And uppercase N is the total number of observations, in our case 36. Okay, so this is how that ANOVA table will look like. I do want you to take a look at this, and I want to walk you through a couple things that are different here. So in our effects model we just saw, we had that block term, right? Meaning that so let's say that we do specify a similar model to that in our LM function. When we do run the ANOVA function, you're going to see something like this, where you're going to have a block line in your ANOVA table. And it has to be there. This is what's going to differentiate the analysis of a CRD to an RCBD. is on the CRD, we do not have blocks, so you would not have a block term in your model, and therefore not have a block term in your ANOVA table. In an RCBD, you do, right? So this block term has to appear there. The way we calculate degrees of freedom is basically just doing the total number of levels minus 1. So we have 4 blocks minus 1. We have 3 degrees of freedom being consumed to calculate the block effect. We do have some squares for it. With a randomized complete block design, we normally do not test for the block effect. Or at least like we're not going to see this ratio here. Well, let me rephrase that. That actually depends, now that I'm thinking about it. So the way that we're going to go through this exercise of the RCBD is to treat block as a fixed effect. We have not talked about fixed and random effects yet, so I don't want to complicate things too much at this point for you. But in our case, treating as fixed effect, we will actually have a block term in our ANOVA with the mean squares and an F ratio and a p-value. If we were to treat it as random effect, which is another option, you may have heard of this, then it would not appear in our ANOVA table. So for now, I'm just gonna say that, yes, we're gonna have a block term with a p-value in our ANOVA table when we do run the exercise, because we're treating the block as fixed. And we're gonna talk about fixed and random effects later, in a later lecture. So we do have the block effect, we still have the nitrogen rate, potassium rate, and interaction between them. So this has not changed. It's the same as before. Now our error has changed slightly. So the formula to calculate the error now is different than what it was for an RCB, for a CRD, sorry. And if you notice, really the only thing I want you to notice here is that now our error has 24 degrees of freedom. And if you remember for the CRD, it was 27. So what happens here is we're assuming we still have the same number of experimental units, same number of reps, same number of treatments. So now we're just partitioning the total number of degrees of freedom differently. Where are the 3 degrees of freedom that were here before on the CRD? Where are they going in this case? Block, right? So we're consuming 3 degrees of freedom that otherwise would be in the error term to calculate the block effect. And this is the main reason why, if you have homogeneous experimental material and you do run an RCBD where you could have run a CRD, this is where it can slightly hurt you, because you're consuming degrees of freedom to calculate the block effect. And if you do not need a block there, then your block effect is going to be highly non-significant. So imagine a p-value like 0.9, meaning that you did not have to have block there. And if you're going to do the same study in the same place next year, you could have run this as a CRD. You could run this as a CRD next year. And instead of consuming this 3 degrees of freedom for block, which is not significant, you don't need block, they would go into the error degrees of freedom, which, based on what we already talked about in previous lectures, the more degrees of freedom in the error you have, the greater power you have, right? Because that's going to make your F ratios larger. And larger F ratios have more power or indicate more significant effect of the terms you're actually testing. So, however, there is a trade-off here. So you're consuming, so let's say that you have a study where you did need to have blocks, like the example we gave with the different soil types in the background. In that case, if you ran a CRD, it would be really bad, because a lot of the variability coming from the soil would actually be confined within either the treatments or the error, and you could not separate that. So now you either have very inflated variability in your treatments or in your error, which does not help us. And so if you do have variability, you do use blocks, you are consuming, yes, 3 degrees of freedom that would otherwise be in the error. However, your hope is that those 3 degrees of freedom that we are consuming are, the effect of that is relatively smaller to the effect that how much variability the block is explaining now. Because imagine the block is like sucking this variability from soil type into the block, because that's how we assign the treatments. And if you did not have block there, if you did not treat it as a randomized complete block design, all that noise coming from the soil type would actually be reflected actually in your error. So you have a lot more variability in your error, unexplained, and that hurts the other tests you make on your treatment factors. So I guess just wrapping up or summarizing that overall comment is, if you have heterogeneous material, you use blocks, yes, you are consuming three, in this case, 3 degrees of freedom to estimate the block effect, but you hope that that block effect is actually sucking up a lot of the extra variability that is coming from soil type into it. So it's removing that from the air and also from the effects on the treatments. So even though you're decreasing the degrees of freedom of the air, you're still explaining a lot of variability with the block effect, and that helps us. So that's kind of the trade-off here that we're talking about. So this is the actual ANOVA table from the data that we're going to be analyzing. It's the same data set as before. And the only difference here for you to notice is that now there is this wrap line here, which in this case, wrap means block because it is an RCBD. We see that it has 3 degrees of freedom. And we see that in this case, p-value is 0.09. So there is a marginal evidence that blocking was needed in this case. And then we still have all the other effects that we had before, and also notice the residual degrees of freedom has been decreased because 3 of those, it was 27 before, we're consuming 3 to calculate the block effect. Okay, so in summary, RCBD is this type of design that we establish one restriction in randomization, and that is the block restriction. And it's not just the restriction itself, but it's also placing the blocks within. So if a block should be within homogeneous experimental material, different blocks can be in heterogeneous experimental material. What we do not want is do an RCBD and have your blocks going like horizontally on that plot, on that map that we saw. Because then the same block would be comprised of plots within different soil types in that example. That is actually the worst that we can do is do that. So having blocks where each one of the blocks is confined totally within homogeneous experimental material is very helpful in this situation. And so we have that one restriction of randomization, which is at the block level. As we saw, each one of the terms of the effects model has a row in the ANOVA table. So now we have a block or wrap effect in the effects model that translates into a row in our ANOVA table. And running RCBDs is not free. You do consume 3 degrees of freedom from the air. However, our hope is that the trade-off or that balance is that we're consuming 3 degrees of freedom, but we hope to be explaining a lot of variability within that consumption of 3 degrees of freedom, which is going to be a net positive effect on your results. That's what we hope that RCBD is doing. And I guess that's what I just said right there. So, all right, so this wraps up our lecture. So now let's get to our exercises. So a couple things that I want you to do, and as a reminder, if you do need some instructions, you could come to the website on the lecture we had on Git. If you open that, there is a refresher here of how we set up the projects for new, or how we set Git and GitHub in RStudio projects for new exercises that we do in class. So if you come here on slide 4, those are the instructions on what we should do. So I have done this already on my side, but we do want to start on GitHub and then let me take one step back. We do want to start on your personal GitHub account, where on your account, you create a directory. What I want you to do is create a directory that this time is going to be called 04_RCBD. So that's going to be the only difference from these instructions, is that the name of the directory, the name of the repository on GitHub is going to be 04_RCBD. So if you come there, you click on new, you're going to say 04_RCBD. And then you can just follow the instructions on these slides here. I'm not going to redo this because I have already done that on my side, but make sure you do all this. And then it's going to show you how to clone that repo in an RStudio format. So you can complete that until this point, until slide number 5. please look on your computer, as, you know, there are a couple slides and I cannot show both of them. So follow these and create a 04_ RCBD on GitHub, and then clone that to your computer. Make sure you follow these instructions because it's gonna tell you where to do that, in what folder. Once you do that, you do go to your forked and clone copy of the class GitHub and do a git pull to get the updates. When you do a git pull, there's gonna be on that 04 class code folder, there's gonna be two scripts we're gonna be using today. They're both named with the date of today. So 0208, one is randomization, one is RCBD. While you do all that, I noticed that I forgot my charger. So I'm gonna go up to my office to pick it up, and I'll be right back. And then when I come back, we can check how you're doing, and if anyone needs help, we can do that. But just as a reminder, so this lecture that I'm looking on right here is the one on our website under the January 23rd, the installing Git class. This is the lecture. That's the one that has the instructions on how to create the repo on GitHub, clone that to your computer, and so on. All right, I'll be back in a minute. It's, I mean, that would potentially help you, but it's not gonna hurt you. So, I mean, I would say, don't worry about it if you forgot to do the git ignore. So as you're doing this, I just want to, connect to the end, right? So once you do create on GitHub, and then you go to the second slide here and follow these directions to clone. Right, so we would do a file on our studio, we would do file, new project, version control in Git. And you would then create this, navigate to the level of the overall folder of the class. So once you do a git clone, you should see something like this, where you have the 01 intro wrangling, the 03 CRD, and the 04 RCBD at this level of the main course. And once you do that and you go inside this folder in your computer, you're gonna have the rproj, you're gonna have the README. I do want to ask you to create the code, data, and output folder. So remember, this is always what we're gonna be doing with a new project. We always want to have those subfolders there. Once you create these subfolders, you're gonna launch the other RStudio project where you have the 2024 DSA. You're gonna do a git pull. I can show you that on my side as well. Oh, I guess on my side, I don't have the rproj. to really show you how that would be on there, but I can show in a different one. So you launch your 2024 DSA, do a git pull to get the updated scripts. Right, so come on Git, on the Git tab. Of course, in my case, it's showing 04 RCBD as the project, but in your case, you do want this to be the 2024 DSA. You do a git pull by clicking on that down arrow. And then on your computer, if you go back to your files, you should see on your 2024 DSA under the 04 class code, you should see two scripts that begin with 0208. And those are the ones I want you to copy and paste inside of the code folder of the 04 RCBD. So once you have done all this, the way that it should look like on your site is on your folder structure in your computer, you should have the 04 RCBD folder. If you go inside of it, you should have the rproj, you should have the code data and output and also the README. And inside of the code folder, you should have copied and pasted the partial scripts for today. I have more than you do because I have the completed versions of them already, but you should have the partial ones that I shared through GitHub. Okay, I'm gonna give a moment here, just to make sure that we're all on the same page. If you were not able to do this, let me know. I can help you. Maybe your neighbor can also help you. So yeah, so there are two repositories that we're talking about, right? So the 04 CRD is the one that you created on your GitHub account that you're cloning, right? And then once you clone that to your computer, you want to create the subfolders code data and output inside of the 04 CRD. And once you do that, you want to open another GitHub repo. So the 2024 DSA that we forked and cloned. So that's the one from the class. That's the one that I shared the scripts and data with you. So you want to open that RStudio project and do a git pull. So we get the updated partial script versions and then move that inside of the code folder of the 04 RCBD. Does anyone need help or maybe run into issues and could use some help? Online, if anyone has any issues, please let me know. Do you want me to see your screen or? Okay, so let's walk through that again. So you already did the GitHub step where you created there, and then you already created a project where you did new project, Git, and this. Okay, so you already have the 04 RCBD in your computer. Okay, so once you have that, This is what you would be seeing, I hope, in your main class folder. So you still see the other previous projects, and now I have the 04 RCBD in that same main class project or folder. If you go inside there, you're gonna have the RCBD project and the README, but I do want you to create the subfolders code, data, and output. And once you do that, now we're gonna have to go to the 2024 DSA, RStudio project. You launch that. And then you're gonna come on the Git pane and click on the pull button. So when you click on the pull button, it's gonna bring down the new updates. So the new scripts that I uploaded that we're gonna be working with today. And so those scripts you download to the 2024 DSA, but now I want you to copy them and paste them inside of the code folder of the 04 RCBD. So you can start working on them on your project. Yes. Oh, yeah. I mean, what I would say is you can just, because like, it doesn't really matter. Once it's on your computer, if you move that folder around, it's not gonna forget. So what I would say is just move this for Yeah, that's fine. It's just I really had that because you did the file that like location.
Yeah, like I used to get this one day and then I getting it installed the right drivers, like interfaces are very good, and like I think they kicked it out. Because like what running fix that is like you have to put sample information, it's like copy that like really for data validation.
I get that on me that you
So we can look into it. Like, I remember.
unrecognized. But the standard error is because in some of the I didn't reply.
Yes.
In some of the blocks, I didn't reply after. So the standard
Like, think about it, because Windows 8, we are, I think that's all that we need. I think it might have been because I forgot. Yeah, because I remember when I said on my PC, like, what was kind of okay, but I got something running. It's okay. I mean, properly, so I remember there was something about it. And I think I had to like,
I have to ask you. No, yesterday I got an email that.
I think I'm using it. Basically, whenever the again, you'll see it real time on your PC screen and then you look at and then I.
Well, so what I proposed was taking it 04 RCBD.
Then you have to reset it on the. You run a new sample and click the button to log in. I think, yeah. And have a template, but I don't think it's required. Yeah. Logan, you always have to blow it out. But I say, like, if we can check it out and see maybe it's gonna be working. I think password
Okay, so I think, well, was someone not able to, so for you to be ready to roll, you should have the 04 RCBD project launched. And in here, if you go inside of code, you should see your two partial codes in here. So if you do see them, let's go ahead and launch the randomization partial. So if you do launch that, you should be seeing it pop up on the left side here. So let me ask this, was someone not able to do this process? Okay, I don't hear anything, so I take that as everyone was able to. This process here, I just want to remind you, so every time that we work on a new topic, I will go through this step, right? So I will ask you to create that name, that the new topic is gonna be, let's say 005 split plots. I do want you to create on GitHub first, clone that to your computer, create the data, code, and output subfolders. And then on the 2024 DSA is where I would share this new scripts and data sets if needed. So you need to open that one, do a git pull, so you bring those changes to your computer, and then copy those scripts and or code or data to the appropriate subfolders of the project we're working with. So code goes in code, data goes in data, right? So this is a typical workflow for everything else we're going to be doing. I know today was the second time we did it, and the first time we did, it's been a while, so we were all kind of rusty. But just for your reference, we do have those instructions on how to do it on that presentation, on the Git presentation. So if you do, and I always have to refer to them as well because I don't do this every day. So I always refer to those to just remind me of the process. But this is what that we're going to be doing this a lot for this course. So it's important that you do get used to doing that. All right, so let's start with the coding side here on the randomization aspects. So this is something that I had planned to teach you before we actually did the CRD actual data analysis exercise, because really this step here happens before you collect data, really. Like you should randomize your study before you implement it, right? Because you have to know where things are going before you go out and apply or plant or do whatever. So this step should happen before. Maybe for this growing season, you could apply this script to your studies right now if you are planning to do randomized studies out in the field this season. So I want to show you here how to randomize treatments to plots, both if you're using completely randomized design or randomized complete block design in R, and then how to make a plot map with using this. When I say plot map, I don't mean a map with like a background, it's exactly in the place, the location where your studies are going to be. It's just like a field layout where you have plot numbers, treatments, the plots are colored according to treatments, things like that. So that's the type of plot map or layout that we're going to be making today. All right, so as usual, we just load the first chunk here. We're just going to load our packages, and today is going to be really tidyverse related. We're going to be doing some wrangling, some ggplot, and that's all within tidyverse. So we're just loading tidyverse for this exercise. And just as a reminder, our treatment design that we are using here is that 2A factorial with 3 levels of nitrogen, 3 levels of potassium. So we have a total of nitrogen treatment combinations. I really want to show you how I do this on my side this is the process I go through when I'm randomizing my studies. Perhaps there are other ways of doing this in R. Perhaps there are ways that you can do this with like one function from a given package. I'm not going to show you that way because I do want to show you a way that's more flexible, so you can adapt to your needs as may be required. Okay, so the first thing that I want to do here is come on this chunk that I'm calling treatments or TRTS. The first thing that we need to do here is create a table where I have all my 9 treatment combinations listed, right? So one column, that's all we would need, where we have all of our treatments listed there. So to do that, one way we could do this is just do a data frame, and then we call like a column with say treatment name, and then we just give 9 different values. That would be the easiest way, perhaps, but not the most efficient. So I want to show you a more efficient way. So in dplyr, I believe there is a function called crossing that we're going to use. So here we're gonna give the name of the columns that we want to cross. So the first one, to keep with the notation that we've been using for this data set that we're using as an example, I'm gonna call that nrate underscore kgha. I want to give it an equal sign and then the C function because I want to provide the levels. So the levels, if you remember for nitrogen and is right up there on the script are 0, 100, and 200. Now, if you get outside of that C function, but before you get outside of the crossing function, so when you are when you are writing between those two parentheses, add a comma, hit return to break the code. But let's give it the other term. So that was potassium rate, so K rate underscore kg hectare equals to, and then the levels inside the C function. So the levels are 0, 30, 60. Let's go ahead and run this. So you should now have an object called treatment TRTS on your environment. And if you print this, you're going to notice that you have 9 rows with all the combinations between the different levels of N rate and potassium rates, right? So this is an easy way for you to get all those combinations. Imagine that if you have more levels, if you have more factors, it becomes ever increasingly more difficult for you to do all the combinations by hand. So by using this crossing function, you can get all the combinations between whatever columns you give inside the crossing function. So let's say if I had another factor here, let's say it was, I don't know, phosphorus rate, I could add that here and then I would get all the combinations, all the 3-way combinations across all 3 factors. Okay, so we have this data set here with nitrogen rate, potassium rate, and all the combinations between among
Got
the.
the best us?
Yes.
I don't know why, but I was just error in C, parentheses 0, 30. I'm just having an error for some reason.
So what I would say is make sure your C functions are opening and closing. Make sure that you have a comma in between the N rate and the potassium rate. Make sure your values inside the C function are separated by commas as well.
Yes, sir.
That is probably the most common mistake that could happen in this case.
Everything looks the same to me. I'm sorry, I don't mean to hold everything up, but I'm gonna retype it real quick, and if I still have issues, I'll let you know.
Okay, yeah, let me know because yeah, I guess we're gonna need this to keep going. So if you cannot do this, you're not gonna be able to follow along. So let me know if it doesn't work, and then you can share your screen and we can take a look at it. I would imagine it's something simple because there's not a lot of dip or complexity yet to the code. So let me know if you need any help. Okay, so one thing I want to do here, and it's going to make more sense why we're doing this when we go to the next chunk, but I do want to create a column here with treatment number. So the more treatment combinations you have, it may start becoming more difficult to refer to them. So you may just decide to give them a number from 1 to 9 in this case. I do want to create that column here. So add a pipe, let's use the function mutate. I want to call this column here TRT-MUM for treatment number. We're going to give it an equal sign. And the way that we can so I could come here, there's a few different ways we could do this. But what I want to propose is that we use the colon symbol here. So going from 1 and then colon gives you like from 1 to something. And that something is going to be, we're going to use a function here that's called nrow. And then we give it a dot. So what's happening here is that it's going to first run this function nrow on the whole data set, and it's going to return a number 9. And so it's going to say, do a sequence from 1 to 9. However, this number 9 here, we could say 9 if we wanted, but the nrow makes it more adaptable to your case. So you don't have to be editing that number necessarily. So if you go ahead and run that, and you print it, now we have a treatment number column going from 1 to 9. Let me see, somebody. Okay, nice. Good deal, Austin. Okay, so we have this new column here, treatment number. The next thing I want to do is something that we have already done in the previous script, which is to create a treatment name column. So right now we don't have a single column where we have the nitrogen and potassium rate combined. I do want to do that next here. So let's add a pipe. We call the mutate function. I want to call this TRT name, is what we've been calling it. If you remember, we were using the function paste 0 to combine values from different columns. So paste 0, the first one I want to have here is nitrogen rate kilograms per hectare. I give it a comma, open and close quotation marks, and give it a plus symbol. Give another comma, and then potassium rate kilograms per hectare. So if we run this and print it, now we have a column that we combine the N rate and potassium rate for each one of the treatments. So we have not only a treatment number column that we can refer to using that number if we wish, but also a treatment name column that is fully informative of what that treatment actually means. Okay. All right, so at this point, we have not done any randomization. We just defined basically our table of our treatments, right? And some descriptors of those treatments. Now, the next step here on the next chunk is where we're actually going to randomize this. And I do want to ask if anyone has any issues at this point, because you're going to need to have this correctly to move forward. Yes.
It's not using the dot
In here,
yeah, it says object.
are you using the pipe? Do you have a pipe here afterwards? Is anyone else having that issue?
I used a different pipe.
Oh, okay. Interesting. Let me try that. You know, I don't use the other pipe normally, so I guess I haven't run into this issue, but let me try to reproduce. Yeah, it must be a difference in the pipe. So in your case, you can either decide to use this pipe, or you can just come here. I mean, I'm sure that the other pipe has some way of making this work, but for us to not spend a lot of time on something simple, you can either change your pipe, or you can come here and say 1 to 9. That would it will work as well. All right. Okay, so we do have our treatment table, but notice that we don't have, so this is just the treatments appearing once, but we don't have them replicated according to the number of reps that we have, because that's really what we're going to need here to randomize. So let's go ahead to this next chunk here and let's do that. I do want to call your attention to something here. If you have not seen this in programming languages, at least in R, this is called set seed. And even though the name is not very intuitive, but what this means is that whenever we run something in R that has a random number generator aspect to that function, it's gonna run whatever you're asking randomly, and that random number is gonna come randomly from a given table of random numbers. That was a very confusing sentence. What I'm trying to say is, behind the scenes, R and other languages have this kind of think of a table of random numbers that whenever you run something random, it will pull one of those numbers or one of those sequences and go from there. And each time you rerun a function that has a random component to it, is going to start in a different place in that table, in a way that the effect of the randomness will never be the same on your results. For you to have your random function here give you a reproducible result in a way that if you run this now and you run this again and tomorrow and next month, you would always get the same randomization results. We need to set seed, which basically is just setting the position on this random number generator table to something. And this something here, I just typed 930. It was, I just like typing out of no specific reason, this number. It could be any number, right? It doesn't have to be 930. It just needs to be a given number that you can refer to every time you run this function so you can get reproducible results out of that randomness of the algorithm. So that's why we're setting seed here, because within this next part of the code, we're going to be generating something random, and that is just to make sure we get reproducible results every time. All right, so this object here, CRD rand, we're going to create and assign the randomization to it. So we can come here, give it the assign symbol, and we're going to use again this function called crossing. So just to remind you here, so the first time we used crossing was to get all the combinations of the levels across N and potassium rates. Now, my goal with crossing is different. I want to get all the combinations of all those treatment names with the reps, right? So what I want to do here is, first I want to type TRT name is going to be the first component of this crossing step. And this TRT name, I want it to be equal to the TRTS object that we created above, $sign TRT name. So basically I'm saying, create a new column called TRT name that basically has the same levels of TRTS treatment name that we created above. That's all I'm saying here. Should be pretty straightforward. And we're just using the $sign to sample, or not sample, but to extract the column of that TRTS object. And then you give it a comma here, give it a couple returns just to break the code. And the other column here is rep. So I want to say rep equals to 1:4. So if we just run at this stage of the script and you print CRD rand, now we have 36 rows because we have all combinations of our treatment names with reps 1 to 4. So this is what basically you can think of all of your 36 experimental units that we have right here. So before we just had each treatment once, now we have each treatment appearing 4 times, 1 for each one of the reps. Okay, so because we're randomizing without any restriction, these plots or these treatments could fall in any other 36 plots. And because it is, so I think, you know, when we did the data wrangling exercise, we were talking about having that we could learn what was the block information just from the plot number, right? So if we do use RCBDs, it is common for you to have your plots as hundreds, 200s, 300s, 400s, where each one of those represent a block, and then the plots would be 101, 102, 103, and so on. In this case, because it is a CRD that we're randomizing right now, it wouldn't really make sense to have hundreds, 200s, 400s, because really that structure is not there. Everything is randomized without restriction. Because of that, I want to propose that we name our plots 1 through 36 instead of 100, 100, 203, just so we have this intuition that it is completely unrestricted randomization. So let's add a pipe there. If you come after this, this comment here, that's where we're going to be creating the column called plot. So we call the mutate function. I want to call this plot. And really what I want to do here, if you think about it, this CRD rand already has 36 rows. I just want to come here and call this plot column with values going from 1 to 36 at this point. So we're going to use the same concept as before. So we give it a 1, colon, and then I'm going to use n row and then give it a dot. Which would be the same as typing 1:36. So if we run that and we print it, now we have this column called plot that's running from 1 all the way to 36, right? So you can kind of think of this as being your plot number that you are assigning to the treatments. Of course, until this point, this plot number has not been assigned randomly, right? It's just following the same sequence as your treatments, which is not what we want. So the next step here is going to be to randomize this. So if you add a pipe there and you come after that randomizing TRT name comment, we're going to use again this function called mutate. we're gonna call plot again. So we're basically overriding. So my goal next is to take this plot column and shuffle it. So we're basically gonna override that plot column. To do that, there's a function called sample that basically shuffles things for us. And we're gonna just say sample plot. So we're gonna take this plot column, it's gonna shuffle everything and assign the result to the same column name, which is gonna basically just override it. So if you run this now and you print it, you're gonna see that your plot column has been shuffled, but just that, everything else remained the same. And just as an exercise of curiosity, so I'm seeing at least 18, 32, 10. If I come and rerun this again, I'm gonna get different results. Because each time you run this, it's taking a different spot on that random number generator table, and you're gonna get a different result. For you to make sure you get the same result every time, you need to run that set seed first, and then run this. So 19, 23, 33. So if I run again, I do need to start the seed again. So set seed again. Then I get consistent results out of that. So it's still random in the sense that it is coming from a random generating process, but it is reproducible. It's starting always in the same spot, right? So if you were to come here and change your seed to any number, really, I'm just going to say 931 instead of 930. This is going to be a different sequence that is randomized. But as long as you keep that seeds the same, it will always give you the same randomness on effect here. All right. And the next thing I want to do here is just to rearrange or to sort all columns by plot. So I want to see the plot number 1 first. So if you come here, we're just going to use the arrange function. We've seen this already. And I want to arrange the column plot. And just make sure you run from the set seed, because each time you run, you're going to get a different result. So this is what we see. So plot 1 received the treatment 0 plus 60. The wrap column here really does not matter. It's just a way for us to create all those replicates on the crossing, but the wrap here does not matter, because I could have, as you see here, I have a wrap 3 right next to a wrap 4, 4, 1, 2. In an RCBD, this does not happen, right? You have all wrap 1s first and then all wrap 2s, and that's the way that it is supposed to be. Okay, so we randomize. In this case, it's kind of like we basically re-randomize our plots. So we had a sequence of the treatments that we created with the crossing, and now then we created a plot column and we reshuffled the plot column. That's basically what we did, in a way that we're randomizing that way our treatments without any restrictions. Okay, so the next thing here is I want to create this plot layout or this plot map. Before we do the map, before we do the actual ggplot, we have to play a little bit with this, do a little bit more wrangling on this shuffle data set. So if you come here on the CRD layout _layout, that's the object name that I want to have and assign the next step of the wrangling. So let's start this off with the object that we just created above, which is called CRD _rand. If you just run that, this again is that table with 36 rows, where each row is an experimental unit that was assigned to a given treatment, all non-restricted. So for us to make a plot out of this, we need to define a column that's going to say row and a column that's going to say col. So basically, we need to define row and column. Imagine that you have a map and you have this grid, right, of plots. We have to define how many rows we have, how many columns we have, just for visualization purposes. This does not mean block. We're talking about CRDs here still. So it does not mean block, but it's just the position of these plots in the map. So give it a pipe there. If you come after the comment here, the first thing I want to do is use the mutate to create a column called row. So in my case here, I want the rows to be, let's see. I think I'm looking at my code and trying to remember if this makes sense, but I think my rows are going to be the different blocks. So what I have here in my code is using the function rep. So this function rep is going to repeat a given number of times. What I want it to repeat are the numbers 1, 2, 3, 4. So I give it 1:4. And the way that I want this is it has this argument that you can change that I want to call each. Each is the name of the argument. Each equals to 9. So if I just run this part here, the wrap 1 to 4, each 9, just so you see what that makes, this creates this sequence where it repeats the number 1 9 times, and then the number 2 9 times, and number 3 9 times, and so on. So this is the sequence that I want to be the row position of the CRD layout. Right, so that's what it did. Assuming that in my field, I have, this space to have, to still have 9 rows and 4 columns. The next thing I want to do here is create a column. So let's add a pipe. We're going to add another mutate and say col for column. And this is going to be just a little bit more complicated than the row. And you're going to see why. So now the columns, I want to have a sequence. For that, we use the function seq for sequence, where it has this argument called from. I want from to be equals to 1. It has another argument called 2. I want 2 to be equals to 9. And then it has another argument called by, which is the step size of the sequence, which I want this to be equals to 1. I want to just run this seq function so you see the output of that. So this basically gives me this 1, 2, 3, 4, 5, 6, 7, 8, 9. I guess we could have used also 1 to 9 as we used previously. But I just wanted to show you a different way of getting that same result. And now I need to repeat this 4 times. So to do that, we come right before the seq function, and we're going to use again the wrap function. So you can imagine having the wrap function. So now we're going to have a few parentheses here, and I do want us to understand what's going on. So I'm running this seq function, which let me change my parentheses to make it easier for you to visualize. So this first parenthesis here is closing the seq function, which is the first argument then of the wrap function. So imagine that it could have been 1 to 9 as we did above. I just wanted to show you a different way. Now the second argument here, so after you close the parentheses of the seq function, add a comma, and it has an argument called times. I want to say times equals 4. And I want to run this so you see the difference between using the wrap function with times and using the wrap function with the argument each. There's a difference there. So if I just run this wrap that is going from 1 to 9 4 times, this is what I get. 1, 2, 3, 4, 5, 6, 7, 8, 9. So 1 to 9, and then repeat it again, 1 to 9, and then 1 to 9, and 1 to 9. That's what you get when you say times. If you say each, you get 1, 1, 1, 1, 1, 2, 2, 2, 2, 2, and so on, right? So that's the difference here between saying each and times. If you did get all of your commas in the right place, your parentheses in the right place, and you run this, you should see this output where you have, so your row column has the sequential numbers, like first all the ones and then the twos, and then your column function has 1 through 9, 1 through 9, 1 through 9. And again, this is just for the visualization aspect. Has nothing to do with randomization. It's just so we can visualize this in a map. Okay, was everyone able to do this? Yes.
And you say like column must be size 36 or 1, not 9.
Okay, is that so is when you ran until here, so this is a good example of how I would troubleshoot a pipe flow. If I run this and I get an error and I don't know where the error is coming from, what I would do is stop the flow by commenting off that pipe and running this. So this runs and stops right here. If I run this and I don't get any issues, I open the pipe again, let it go to the next function, and then run it. And if I get the issue, then I know it is within this function. If you do that, can you identify which one of the mutates or you have an issue? Okay, so make sure that you have. So all of this is basically the first argument of the wrap function. So make sure that you have the sequence. Make sure you have your commas in the right place. Make sure you're closing the parentheses of the sequence function right here. Maybe you're missing this parenthesis right there after the by equals 1. Okay. Awesome. Yeah, because sometimes a mistake that I run into sometimes is, let's say if I don't have this parenthesis there, but I add a third parenthesis in the end, it doesn't yell at me saying that I'm missing parentheses. But if I run it, it doesn't work because then it doesn't understand where a function ends, where the other starts. So you need to have them the right number, but also in the right position. Okay, so lastly here, before we actually plot it, I want to add a pipe. You come after this comment here. We're just going to do something we have already done a few times, which is to create a column that's called treatment name. So we do that mutate, TRT name equals to, we're using that function pay 0, where the first argument is going to be, actually, this is actually not exactly what we used to do. This is not for treatment name. This is for a label. So instead of calling treatment name, call this lab for label. And what we do want to do here is paste 0 the plot information, give it a comma, open and close quotation marks. We're going to use this notation of /n. So this is to break line. Whenever we have a text string, we add /n. It breaks the line of that string. And then add a comma. And the second thing I want to do is give it the treatment name. So this is going to work because if you run this and then you print it, this is what we get. And even though in a table format, it doesn't make sense, it doesn't look nice, but when we create a geom text or a geom label, this is going to have number 1 on top and then 0 plus 60 below it. So we know the plot number and the treatment assigned to that plot when we make a layout of this. All right, let's move on to actually creating our plot here. So let's begin with calling ggplot. I want the data to be equals to this object that we just created above. So crd_layout. Give it a comma. Then we start with the AES function. On the x-axis, I want to put the row column. On the y-axis, I want to put the call column. If we just run that, we get this empty canvas because we have not asked for it to add any geoms yet. So we come back to ggplot, add a plus. We're going to use a new geom we have not used yet. That's called geom_tile. If you just run this, let's see what happens. So this is what we get. It doesn't look like what we need. So let's change a few things here. The first one is on the AES function inside of geom_tile. I want to say fill equals to TRT name. If you run that, this is what you get. So notice now how each one of the cells are receiving a color according to the treatment that they were assigned to. I do want to add a outline color around these plots. So to do that, it's still in geom_tile, but outside of the AES, you add a comma and let's say color equals to black. That's going to add an outline. And really, you don't know this yet, but at the end, we're going to have the plot number and the treatment name inside the plot, which means we're not going to need really a legend for the treatments. If you want to keep the legend, that's up to you. I am proposing we remove it just to make more space for the actual map. To remove just this legend, we can come to geom_tile, add a comma, and say show.legend equals false. So that removes just this legend here. Okay, so the next step now is, I want to add some text to it. So I want to add the legend. Let's add a plus after that geom tile and call geom_text. I'm seeing that my code here is actually doing something that I was not expecting. So I will show you what I was expecting. And if that doesn't work, then I'll probably remember, this is why I changed my code. So let's try that first. So I want to add here a text on each one of these plots that is going to be this label here. So the lab column here. So to do that, let's go ahead and call the AES function. So if you remember, geom text has an argument called label, where we say what's the column that has the label that I want to show. The name of this column is lab, as we created that column just on the exercise above. This is what it shows up. I do want to make a few adjustments here. So one of them is I want to change the vertical adjustment. So we come outside of the AES and we type vjust for vertical adjustment. I want to say that equals to, let's do that equals to 1 and see how that goes. Okay, I think that was actually not a good idea. Let's try minus 0.5. Yeah, that it seems like it's not placing in the right place though. Maybe, let's see, if we do just 1. So I had this, maybe this is why I changed my code and now I'm realizing the reason. 0.5, so not negative. Yeah, maybe that's a better option. Yeah, thanks, Anis. Okay, so let's keep the vjust as 0.5. I do want to add a title to this plot. So to do that, we can add a plus. There is a function called labs, if you recall.
Dr. Bastos,
Yes.
can you explain again why we're doing that vjust and adding the 0.5? I don't think I follow you there.
Yeah, so the vjust is just changing the vertical justification of the label. So if you change this number here to, let's try 1. It's just moving it either upwards or downwards. And we're just trying to find a number that puts it kind of in the middle of that plot.
So, but what if like your plot number and then your rate's already like in your plot, like, because originally before you had it at all, like I was talking about before you had vjust at all.
Mm-hmm. That's right.
See, mine looks, is it just to get everything like smooth in there?
Yeah, let's see. I think if we do vjust equals to 0.5, if that is the same, I think that's actually the default value is it must be 0.5. Yeah, I think in my code here, I had a slightly different code. And I was changing this number, but I think if we just keep the default value, which seems like it is 0.5, it should work as well. Yeah, does that answer your question?
Well, I think so. It's just so like mine just like before I even add vjust, it looks very symmetrical already. Like it's got like yours looks like it's like hanging down a little bit or like not perfectly on the line, and mine is. And I was just like, I didn't understand why we needed if it was already set up good.
Yeah, I mean, if it's already looking, properly on your side.
Yes, sir. Like mine's not bunched up like that. Just was my point. I didn't know how anyone else was.
Yeah, because that's also going to change whenever we export this plot here as a figure. The dimensions we give to that plot is going to determine how the text looks like. But so that vjust is just to make it more symmetrical within
Okay.
the plot.
Yes, sir.
But if you're already getting that, then you don't have to worry about it.
Yes, sir. Thank you.
Awesome. And before we give a title, I wanted to give a title here on the labs function. But before we do that, I just want to point something to you. Normally, you would start your plots would be 1 starting on top and then moving downwards, which is not what's happening here. It's kind of like going from bottom up and then bottom up, bottom up, bottom up. If we just wanted to flip this to have top-down movement instead of bottom up, we would come here, you can come to the AES inside the ggplot level on that y equals col, you can just say y equals minus col. That is just gonna change that direction for you. So again, I just came to the AES where it says y equals col, I just added a minus sign there that just reverted things to be starting at 1, ending on 36.
Professor,
Mhm.
can you go back to the CRD layout chunk?
Mhm. Good deal. Was everyone able to get to this point? All right. So the last thing, or a couple last things I want to do here, one is to give it a title, so it's a little bit more informative. We use the labs function for that. There is an argument called title. You give it open and close quotation marks. I just want to call this like CRD randomization of a 3 times 3 factorial. And if I add open and close parentheses here, I just want to say 9 treatments within it. If you don't want to write all this, you don't have to. I just, on my side, I just want to make that very clear. And then lastly, I just want to change the theme to make this even more clear. So to do that, we can add a plus and then I want to add the theme underscore void, which basically removes all X's and leaves just the map itself. So plus theme void is what we got in the end. Let me just show you my code a little bit in case you're still catching up. But this would be the map that you can now put in a Word file in your protocols. You can take this to the field that you have completely fully randomized your study if this was a CRD, right? So no restrictions. We have here on the labels the plot number, so we know what is the plot number. You also know what's the treatment name that was assigned to that plot number. And just, something to, I guess, notice here is that as we know, as you would expect, because we do not have restrictions on randomization, you could have the same treatments falling on the same column, I guess. So we see here that the treatment 100 plus 0 is on cell 3, is on plot 3, is also on plot 4, and is also on plot 7. So by random chance, it happened that all of those 3 of the 4 reps of this treatment all fell within the first column, as a CRD would happen. If this bothers you and you still want to have like no restrictions in randomization, you can play a little bit around with your seed, right? So like, let's say if I did not like that randomization, I would come to my seed here, actually, I don't know, type whatever other number I want and just rerun everything until the plotting. Because really the plotting is just showing you the result, but the randomization happens all the way up there. So if you just come here and we run it, you get a different result. So we could play around with this. I would not, I guess, encourage you to be playing a whole lot. So you have 1 treatment per column. I mean, a treatment appearing only once per column, because then you're really just forcing yourself to randomly be in a randomized complete block design, which is not the goal. But if you have some room to play with this, I just want to return to 930 so my results remain reproducible. But you do have some room there in case, if by random chance you have all treatments falling right next to each other in sequence, then you may want to maybe here, like this is, I would not want this to happen. So I would play around a little bit with the seed just to not have this happen. But still remember it's a CRD. So to some extent that should happen. Okay, so we have the RCBD randomization now. I think we can probably finish in the next 30 minutes because it's going to be very similar. But I do want to give you a break because we are going to 11:30 today. So let's take 5-minute break. Let's come back at 11 and I'll see you soon. Which one, go into
That's what I mean.
So you do already have this.
Yeah, I created a.
Okay, it's not gonna over here. It's already. On. That is pretty good. I remember seeing that, so I think, actors and, so when you did this the first time, when we did the real 3CRD, did that happen as well?
In companies. But we started.
Actors and, I don't know why, I don't know, where is this spectrum? Because to me, it's, like, one thing I would try, like, to see if it helps, even though I don't know if that would speculate. So what I would say is, what I would try is maybe on your.
It's creating a new.
So you. From vertical control. Facing that. I mean, that by itself, so, and this is in your computer, right? It's not like in OneDrive or something like that. Like, that's also tricky, so. But I guess what is also intriguing is the fact that you do not have anything when you're doing, right? So, let's say, Where's the. For me, like, if it is not shown there, here's. And then just generates. So, like, I was trying to find the creative. I mean, you need to click there, just like. Oh, you will bring that before, I think. I think that's. Like, rescue. Yeah. Once you get in, or not, or once you get to be there, yeah, so I'm good. So when that one still issue of the folder, but at least you can, like, you get Chrome, and then link that whole folder into your course folder. And then if it's not showing Git, you can do this to the Git.
When I do it, I would say, I don't, the date. But it's something like European documents, I have. I've done it. Because I have this. Even if it comes to that, we have a
Maybe I would say, what if you tried to shorten the folder, the name of the folder may be too long, or maybe, because sometimes like having white spaces in the folder file names may cause some issues. I would not expect for this to be the cause here, because I have not seen on my side and I have white spaces in my folder. But that would be something I would try a little bit. Perhaps for some reason that can be the folder here, so. Or do the length of the new computer, or the fact that it was white spaces. That might not. All right, so let's continue here with now randomizing our randomized complete block design. I guess before we get there, I just want to tell you, this is how you could randomize and create a plot of CRD design. You know, if you do have a study of your own that you do have the chance of randomizing that for this season, I would say try at least, you know, if you have a CRD, try the CRD code. If you have an RCBD, try the RCBD code. Of course, you're going to have to adapt that to your treatment factors and levels, but it should be straightforward from that point on. Okay, so let's do the same here for our RCBD randomization. So we're going to start off with the crossing function again. So make sure it is the crossing function. There is also a cross function. We want the crossing function. As you remember, the first thing that we did was to create that TRT name column, which is basically, again, the same column that we pulled before. So that's from the TRTS object $TRT name. That's what we want. And again, if I just print that TRTS $TRT name, we get just a list, a vector of all the treatment names. And then we also want to do cross this with the reps, right? So we say rep equals to 1:4. So if we just run this, we again get that the same result that we get for when we started the CRD randomization, that is just treatment names and then crossed with all the reps. So we have 36 rows because we have 36 plots in or experimental units. Now, the next thing I want to do here is just to arrange by rep. That's going to be important because, you know, we're doing an RCBD randomization. So I do want to at least visualize the reps, like all the rep 1 first and then rep 2 and so on. We're going to use the function arrange and say rep. So we arrange this by rep. And just to make clear, this is more just for us to visualize because the randomization itself is not going to be impacted whether or not you arrange the data first, but it's just so we visually can see you know, what is going on there and combine all those plots. Because now remember, on the CRD case, the rep number was really not important to assign treatments to plots, right? It was not important. We just had to know that each treatment was appearing 4 times, and then the randomization was open. Now the rep or block number is actually important because we're going to be randomizing individually within each one of those reps or blocks. So the next step here, add a pipe. What we're going to do is, okay, let me tell you this in words first and then see if you are thinking, if you're creating the intuition of the function that we would translate the language to code. So if I want to randomize separately for each one of the blocks, what do you think we should do immediately next here in this code? Group by, yeah, group by. So we group by, we create that structure that we say within each one of these groups, we're randomizing, right? So we do a group by, and in this case here, the column is called rep, right? So we group by rep. We add another pipe there. And now we want to create this function called, or we want to use this function called mutate to basically within each one of the reps or blocks, I want to shuffle the treatments, right? So to do that, we're going to just overwrite on the treatment name. So right now the data set has just treatment name and rep, right? So I'm grouping by rep and then I'm shuffling treatment name. So we're going to overwrite treatment name. You can just call the same call name. And you're going to use the function sample, right? So sample treatment name. So for each one of the blocks or reps, we are reshuffling the treatments. And one thing to notice is we do know that each treatment is appearing once per block in this case because of this crossing, right? That's what makes this assumption true, is I know that each treatment appears once in each block because I use this crossing function, which basically creates all combinations between treatment names and reps. And because of that, we can just do the simple randomization. So now if you print it, you're going to see there is a table, 36 rows. It has 4 groups based on reps. And now all the rep number one here, if you went here and look individually, you would only find a treatment once and all treatments present in all blocks. Right, so very simple. I mean, we're just using this sample function to do the randomization, very straightforward. Now, there's gonna be another step here that we did not do with the CRD. Or I guess we did with the CRD, but in a different way, which is the plot number. So now, what I wanna do here is I wanna call this first plot, this first row here, I want it to be 101, 102, 103, all the way to 109, and then 201, 203, and so on. And before we did not do hundreds to hundreds, right? We did 1 through 36. So it's pretty simple, say go from 1 to 36, that's it. In this case here, there's the hundreds, or there's that 100 component on the plot number. So let's add a pipe here, let's call it mutate. I wanna ask or create this column called plots. So there is an interesting way here on how to do this that is actually very simple, but I want to ask if anyone has any thoughts. Yeah,
Yes, ma'am.
case when, okay. We could go that route, and that is a valid route. I want to show something else, but that's a good way of thinking. I like that you're thinking that way. But I do want to show you all something that is simpler and very elegant, actually. So how can you use these columns to create 101, 102, 103? Except for using case when.
A unique value.
Okay. So, and I guess I'm not expecting you to know the answer I'm looking for because it's very specific, but I want you to, I guess, appreciate how complex you could be thinking about it and how simple the implementation actually is. So if you think about it, if I have this rep column, that's the block number, right? And I want all the blocks, all the plots in block one to be hundreds. So what I can begin with is just say plot equals to, I want to give open and close parentheses here and say rep times 100. So that's not the end of it, but it's the beginning of it. So if I run this, basically all the plot one are hundreds, and then plot block two to hundreds, and so on. And now, because this is still a grouped data set, I can just say plus 1:9. And that's gonna make 100 plus 1, 100 plus 2, 100 plus 3, and so on. If this had not been a group data set, you would expect you to give 36 values. So 1 to 9 would not work. But it is looking at each one of the groups that we determine at the group by level, and it sees that each one of those groups have 9 values. So if you give 1 to 9 in the group data frame, it works. So by doing that, we basically are assigning the plot numbers here. I do want to call out for one difference between the CRD randomization and the RCBD. If you notice, the CRD randomization, we randomize the plot numbers to the treatments. Because at least the way that I developed this code, I thought it was simpler to do that. When it came to the RCBD, where we have to group by the blocks, it made more sense to first randomize, shuffle the treatments, and then write the plot numbers in sequence. The key takeaway is that you're randomizing one of those two components, right? So we're either shuffling the plot numbers, which we did in the CRD example, or you're shuffling the treatment numbers or the treatment names, which we're doing here in the RCBD case. There's nothing statistical about that. There's nothing like CRD you do this way, RCBD you do that way. It's just the way that I found was easier to implement via code. Perhaps there's a way you can do shuffling the plot number in both. I'm sure there is. But at least the way I developed this and I thought was more efficient and less code was doing this. So go through this on your own time. Make sure you understand what's going on each one of these lines of code. Because I do, this again is a way that you can use to randomize your studies. Once you have the script, which you have now, it should be simple for you to just adapt your studies. And it is reproducible, it is randomized, you get a plot layout at the end. So I think it makes sense. Yes, certainly.
Is it possible that like when you use the same seed set and you got the different lot numbers, different seed numbers?
So what happens is if you set seed one time and you run it, but then you run it again without setting seed again, you will get different results. So if you are setting seed and running every time, you should get the same results, including as myself.
You're getting different from yours.
Oh, you are? Okay. Ah, interesting.
So your first plot is like 0 plus 61, 0, 1.
Okay, interesting. It could be, I mean, I guess I never taught this class before, so I never had the comparison, you know, with other people. Originally, I would expect to be the same, but of course, you're telling me it's different.
The plot.
So it may be related to the way that in your computer, maybe there's a different version of R or Studio or a package that determines a different position of that seed on that table. But really, my goal is as long as it is reproducible for you, that's what matters. As long as you run this 3 times or n times and you always get the same output, that's what matters. I'm not worried if yours is not like mine. But thanks for bringing that up. I guess I was not expecting it. Okay, so lastly, what I want to do here is something to pay attention whenever you use group by is actually a key point here. So the only reason why this worked is because it was a grouped data frame. So, and we know it is a group data frame because we did a group by. When you print it, it tells you right there is a group, there are groups, right? So in this case here, it was good that we had group data because we could just use this notation here. But sometimes having grouped data frames carrying over in your analysis may have consequences that you're not expecting, and then it's harder to troubleshoot that whatever's happening is because you have a group data frame. So what I would encourage is that you come here, add a pipe, and let's ungroup this data frame. So we did the operations that we needed at the group level, and now I just want to ungroup it so that structure of the groups does not carry over forward. So if you ungroup it, now you can see that there are no groups defined here on this data frame.
Your is not reproducible up to that.
He's not running from the.
Oh, I'm not running from the top yet. There we go. Now it should be. Oh,
Did it change?
now it's okay. Okay. So probably what happened is when I was running the code and showing different parts of it, I just reran it just to have whatever I was doing in the code to show, and I was not going from the set seed. Yes.
That function that you use, return 100 plus string of 19. We also use the base 0 function there. Base 0.
The pay
For
zero.
example, plot the base
So
0,
if
red
you,
plus 0 plus. Okay, red minus 0 comma 1 to 9.
so here's what I'll tell you. A beautiful thing about programming is you can try and see if what happens,
It
right?
will work.
And my intuition is that that would not work because pay zero, we use that when we're combining strings or when we want to make a string or a character. In this case here, we're doing a calculation, so it has to be numerical, right? So with pay zero, I don't know if you can pay zero a numerical column and have the output be numerical as well. The output is gonna become a string, a character. But that's a good question. That's a good point. Okay. So let's come to the next chunk here. So the next chunk, I just want to prove to you or to teach you how you would check that we do have each treatment appearing once for each block. It's very simple. I left you the code, part of the code there. So we're not going to create a new object. I'm just going to add a pipe. And we're going to do a group by rep and treatment name. And add another pipe, and we're going to call this function tally. So tally is just giving you the number of observations within the groups that you created. Because we're grouping by rep and treatment name, it's going to return to us each combination of rep and treatment name and say an n here would be how many rows are present within each one of those combinations. And you can see here that n equals to 1 all across, which is what you would expect. It means that you have each treatment in each block once. And if you had like a very complex study where you don't want to be relying on visual assessment of this number one, you can just add another pipe and do a filter and only filter rows where n is greater than one. So if you did have something happen on your setup that you ended up having a treatment more than once in a block, and you do this, it would return just that row. In our case, returns no rows, which is what we intended, because we only have a treatment appearing only once in each one of the reps. Similarly, we could play around with this group by. So if I wanted to check how many rows were there in each rep, all I needed to do was just remove the treatment name. I group by just by rep and get a tally. It should be 9 because we have 9 treatments, right? So we're just checking here that the actual result of the randomization did what we wanted to do in this case, which it did. So we confirm that. Now, the last thing is, I left you the code here already. So it's that same code that we're getting. Now that we did the randomization, I'm just getting the wrangling ready for the plotting side of things. If you're not plotting, you don't even need this, right? So this is just getting the rows and columns so it works when we plot it. I left you all the code, I believe. Yeah, I left you all the code, so you can just go ahead and run it. So this, we still have 36 rows, and now we have this row, column, and lab columns. And then on the plotting side, I think I left you all the code as well. Yeah, I left you all the code, so you can just go ahead and run it. And this is what we see. And I just want to show you here, since I left you the code for the second plot, the difference you're seeing here is just the way that we added the label. In the code for the RCBD, I added the label 2 times. So the first time I added just the plot number, and then I made it bold. And that's why the VJust was changing on my side and it wasn't on the live code here that we're doing, because I did differently. So here on the code I left you, I'm adding first the plot number and then adding the treatment name below it. And the reason why I separated these two was because I wanted to make the plot number bold, which you cannot do. I mean, you can bold the whole thing. So I could make bold on the previous CRD example, I could make bold the plot number and the treatment number. But in this case, if I just want one of them bold, you have to separate them out. So this, again, is the randomization for the RCBD. Now, if you do pay close attention, you're going to see that we have these 4 blocks and that each treatment appears only once per block. So we have your plot numbers going from 101, 109, 201, 209, and so on. Also have the treatment names right below it. And this is how you would randomize and also plot an RCBD. Okay, the last thing that I want to do here is just export, show you how I would export this to file. Because if this is the actual randomization for a study, imagine now that, if we just take RCBD ran, for example, this can be the backbone of your data collection now. Because now you can go to the field and you collect plant heights, let's say. You can have an Excel file that's based on this CSV that we're going to export, have that, rename that to plant height, I don't know, V2, whatever, and just add a column there that's plant height, and then you measure it. And then you just keep using this as a template for data collection if you want, because you're always going to have the plot numbers numbered or sorted in the correct form. You're going to have a treatment names if you wish to have that whenever you're collecting data, and so on. And this also helps because if you're using something similar to this to collect your data, when you do bring that data back to R to analyze, you can just do a left join, and then you easily connect your height, yield, whatever you're measuring, with the setup of your randomization already right there. So I do want to export this. This is what I do on my side. I export this and I use this as a template for data collection spreadsheets. So to export this, so right now RCBD ran has treatment name, rep, and plots. I did wish that it would have also nitrogen rate, potassium rate, those columns. So before we do export this, I want to do a left join. So let's add a pipe there. You come after the comment here. We're going to use a left underscore join. And the object that has all that extra information is called TRTS, the one that we created right in the beginning. So if I just print TRTS, It has N rate, potassium rate, treatment number, treatment name. Because we're using left join, have we used left join in this class this semester already? No? Sorry, I'm teaching two classes and sometimes I get confused with what I teach in one and the other. So, okay, let me take one step back here and just talk a little bit about left join. So left join is a very, very powerful function or joins in any programming language. In this case, specifically left join is a very important function when you're trying to merge two data sets that have one common column and common levels under that column. What do I mean by that? If you look at RCBD rands and you print that, it has 36 rows and it has this column called treatment name, right? On this TRTS object, I also have treatment name, and I only have 9 rows in this case, but it is the information for my individual treatments, right? So even though they're not even matching in number of rows, but I have one common column, in this case, the column name is the same, treatment name across both data sets. And not just that, but the column values are also the same across both of them. So in this case, my goal is to take this RCBD rand that has 36 rows and add here the nitrogen rate and potassium rate information that is actually found on another object, is the TRTS object that has that information. And you notice that they have a common name, a common column that's treatment name. So by doing a left join, it's basically going to take whatever is on the left side. So on the left side is what's coming first on the pipe, and join whatever is coming on the right side to the left side. If they have different row numbers, like they do, the first one has 36, the second one has 9, it's just going to repeat the values where it sees that there is repetition to do, right? So in this case here, TRTS does not have rep information. It would be just like your treatment table without reps. When it left joins to RCBD rand, and he sees that the treatment name 0 plus 60 appears 4 times, it's just going to give the same 4 nitrogen rates and potassium rates by it, right? So it's an easy way for you to merge two data sets that are separate, but that you have pieces of information on both that you want to combine in one. Left join is very useful for that. So if we do that here, you end up with 36 rows, which was the original number of rows of RCBD rand. And RCBD rand only had treatment name, rep, and plot. So now we have nitrogen rate, potassium rate, treatment number as well. So left join helps us to do that very easily. Sometimes what I guess I've done in the past and I've seen people do as well is either do that by copy and pasting, right? Or maybe you arrange both data sets by treatment name, and then you just, again, copy and paste TRTS information 4 times to make a match. That could work, but that leaves room for error, right? It leaves room for human error. Left join does that operation for you without the chance of human error. Okay, so the next thing here, I just want to rearrange and select some columns. I want to use the function dplyr or function select from the package dplyr. So we do dplyr :select to make sure that this function comes from this package. I just want to, so looking at the current order of things here, I want to have first plot number is going to be the first column. Then I want to have rep, so the block number. Then I want to have the treatment name. Treatment number is the next one, so TRT num. And then I want to break code just to make it easier to read. I want to have the N rate and the potassium rate as the last columns in this data set. So they are ordered in a way that has some hierarchy to it, right? And I guess to me, at least to me, it makes sense that would be plot, rep. Perhaps rep could be the first column as well. Yeah, it's subjective, but I'm just showing you one option of how you could reorient these columns. And then lastly, we just add a pipe and use a write_CSV to export as a CSV file. Because it's coming from the pipe, we don't have to specify the object name. We're just going to give it a path. So I want to open and close quotation marks, get outside of the code folder, // I want to go inside the output folder, and I want to call this RCBD _randomization _table.csv. Remember that we give the extension inside here as part of the file name. So if you run that, and you come on your Files tab, R blue button, go on Output. You should see now an RCBD randomization table.csv that then you can use for your actual data collection, creating your sheets for that. Okay, and also assuming that, you know, you are doing a RCBD and you do want to have that plot layout exported to file as well. We've used DigiSave in the past. I left you the code here already. So the way that DigiSave works is gonna save to file the last plot you printed, even if that plot is not printed in the same chunk as DigiSave is. So the last plot that we created was the RCBD one. So if I come here and add DigiSave here, I'm exporting to output. I'm giving this name RCBD layout map.png. I'm changing the width and height to 6 and 4 and making the background of that plot white. If you just run that, you go to your output folder, you should have this RCBD layout map where it has all of your treatment layout, your study layout. Okay, just another last point here. So this is something you do before you start your experiment, right? So the workflow that we talked about in the beginning of the class, as far as setting your hypotheses or objectives, looking to your experimental material, determining experimental design, determining treatment design, and then do randomization. So this step would happen right after that. And then after this step, then you're ready to go and implement your study in the field, start collecting data, and so on. And then while we're going through the analysis of the CRD and next Tuesday, the RCBD analysis, that's what happens after you collect the data, right? That's just an example of how this flow would work within a research workflow. Okay, we have a couple more minutes. I do have some announcements. Let me look at my to-do list to make sure I don't forget about them. Okay, so we have an assignment. So I uploaded this earlier this morning, I guess. So if you already pulled for this class, you already have the files on your computer. It's called assignment 3. Let's just go there and take a look at it very quickly. It's under 02 assignments and it's called assignment 3 CRD. So I'm giving you a QMD file and also a new data set. I basically am asking you to reproduce the same analysis we did in class, but with a different data set. And what that means is, you know, we talked about some decision-making in class. So things like, do these residuals look good or not? Should I look at the main effects or interaction? Things like that. It may be different for this one. So do not simply copy and paste code, but think of what you're doing. So you make sure that you're understanding the flow of those decisions. I just opened that file here so we can look at it. So we have not fully talked about quartile files in this class to the full extent of it. One of the reasons why I like it is you can render very easily to HTML. And that's what I want you to do. So this part of the code here has some information about how that's going to be rendered. If I just come here and click render, if you do have code, but the code does not have any issues, so if the code is running smoothly, if you render, it's going to render without problems. However, if you leave code with problems that does not run when you try to run individually, when you render, it's not going to work, just so you know. But I just quickly rendered this file here so we can see what that does. It creates an HTML for you that looks like this. So notice that there has a table of contents on the side here. As I'm scrolling through, I see those heading 1 and heading 2 levels that we established on the quartile file. And I have a lot of instructions for you on how to work and submit this assignment. We're running late here. So what I want to do is I just want to take your attendance right now. So if you do have to leave, you can leave. I will keep talking for maybe another 3 minutes just to finalize the assignment explanation. And if you have to leave, that's fine. You can catch up later with the recording. So Okay, so you can go ahead and claim your attendance, and if you can stick around for the next 3 minutes, please do so. If you have to leave, I understand that. You're welcome to leave, and then you can catch up with the recording later. Okay, so as you're taking your attendance, I just want to keep talking about the assignment here. So this is an assignment that you're gonna do at home. We're not gonna have time to do this in class, so it is a take-home assignment. If I come back to that Quarto file that is on the GitHub repo, I have instructions here. I just want to walk you through a little bit of that. So basically, you have a new data set to run a CRD analysis completely like we did in class. So all the way from important data, EDA, model fitting, ANOVA table, checking assumptions, extracting means, pairwise comparisons, publication-ready plots. In class, we did not get to fully finish a publication-ready plot. Here, I want you to do that. So it doesn't have to look at any specific way, but it has to be in a way that whenever I see it, I see, okay, I could see this plot in a published paper. If there's something about that plot that doesn't seem professional, then it's not professional, it's not publication ready. That's how you know. So if you look at that plot and you think, maybe I should change this label here to something uppercase, the first letter uppercase or whatever it is, that's what I'm looking for in this case. But anyway, so I'm asking you here to move this script here, the assignment 03 CRD script that I share on GitHub, to the code folder of your 03 CRD project. So I'm not asking you to create a new project. I'm just asking you to move this script into the code folder of that already existing project. And then similarly, move the data set that I'm sharing with you to the data folder. And I do want to add your name right here. So when you change your name here and you render it, that's going to appear on the render version, like right there, right? So make sure you change your name here. And also I have instructions for you to change your name on the file name when you send to me. So again, this is a Quarto file, meaning one of the great things about it is that you can easily get an HTML professional looking report out of this. It could also be PDF, Word file, but HTML gives you the most interactivity. So I like that. And this is called YAML. It's spelled like YAML. This is the part of YAML is a program. It's a language itself. It's a very simple language that is just used to specify some components of how this Quarto file is rendered. You really don't have to know much about it. I'm not asking you to change the YAML besides just putting your name right there, but I just wanted to know what that is. So if you run into this in the future, you have heard about this at least. Okay, so I left you the steps of this workflow. So if you look on the outline here, you're going to see the setup, EDA, wrangling, and so on. All the steps that we did in class are still in this structure. And sometimes I left you chunks for you to do specific things, and I have instructions of what I want you to do in those chunks. Very similar to what we did in class. I'm not asking for anything crazy here. And I'm telling you, a little bit about this study. What was the objective? What was the design? But notice here on the EDA, wrangling, EDA, I'm not giving you any chunks. I want you to create your own chunks. You're going to determine how many chunks you need and what for. So it's going to be up to you to do that. And I do have some clearly outlined questions here. I think I have 3. So question 1. I want you to, below each plot of the section, write a sentence explaining your visual interpretation of the plots. So if I'm asking a question to do something, make sure you do that. Because if you just show me the plots, you're not going to get full credit for that. You're going to have to make a plot and say, based on this plot, I see that this is happening, that's happening, whatever it is, right? So you need to fully answer this question to get full credit. Just creating the plot is not enough. So a stats model, ANOVA table. I have another question here for you to tell me how you would look at this ANOVA table and decide based on that ANOVA table for this exercise, how you should extract means and pairwise comparisons. I ask you about the assumptions here as well. I have a question about that. And so on. I have some other comments here to guide you and give you some more background as well as far as what I'm expecting. Now, getting to submitting your work, I do want to go through this because it's going to be the first time that I'm asking you to send me an HTML as a product. And that HTML is the product of when you render this Quarto file. So a few points here. I do want to ask that, so as you know, what you can just code along everything like you did what we did in class. You don't have to be rendering each step at the time. But whenever you think you're ready to send this to me, I want you to render, see how the final product looks. And if there's something weird about it that is not looking professional, I want you to change that. Because if you send me something that looks unprofessional, you're going to lose points for that. What are some of the occasions on a Quarto render file, on HTML based on a Quarto render file that could be unprofessional that I've seen in the past? Some tips and tricks here. So if you have any chunks that you print, and I don't think this is the case, but just to let you know, in the other class we have this. We have a data set with like 6,000 rows. If you print that data set in your chunk here on the Quarto, it just shows you the first 10. On the render HTML, it will show all 6,000. I do not want to see 6,000 rows of data. I don't think it's going to happen with this data set here, but just so you know, if you do see there's something wrong, like you're showing way too much, it's annoying to go through that, then you can fix that, right? So in that case, you can use a function like the head function that just shows the first few rows of the data set. That's one case that you can run into. I want to ask you to not delete the structure or even the comments that I'm giving you, because I use those to grade. So if you come here and you decide that you don't want to have this G final plots here, that's going to make it hard for me to grade. And if I'm unhappy grading, you know, it's probably not a good sign. So leave the structure I'm giving you here. Of course, you will and you should write your own comments. I encourage you to do that, but do not remove what I'm giving you because that helps me when I'm grading this. Another thing you're going to notice when you render is that you may have noticed or not on the code that I share with you, but every time you want to break line, we give it, I give it 2 white spaces after that last point, that stopping point, and then hit return. If you do not give the 2 white spaces and just hit return, when you render it, those things may be connected. So if you need to break line on the render version, you can just go to wherever you want to break line, give it 2 white spaces, hit return, that should work. Okay, so the last tip here is, so you probably have seen that when we're running the setup chunk and we're loading tidyverse, for example, but also happens with other packages, it tends to give us some warnings. And those warnings are always going to be there. They're not going to affect anything. But when you render it, think that you're sending this to your advisor or maybe to your boss at a company or something that you want to make sure it looks professional. You do not want those warnings to be popping up on your chunks. For that to be true, let me just create a chunk here to show you. There is a way that you can inhibit warnings at the chunk level. So if I just have whatever chunk, let's say I have here library tidyverse first, and it gives me, well, it did not give the warnings now, but it does give normally. So we can change some options at the chunk level that we begin by giving a hashtag vertical pipe. So there's an option that's called message that you can set to false. There's an option that's called warning you can set to false. By doing this, you will make sure that your tidyverse warnings are not going to come through the render version and it's going to look professional. And then, so after, and this is all once you're done with everything, you know, you render it, making sure it's professional before it's sent to me. When you do render it, it will create an HTML file with the same name of a Quarto file, but just a different extension. And that is what I want you to send me. I do not want to see your Quarto files. I want to see your HTML files. And so you can go to your HTML and add your last name to that file name. Right now, this file is called assignment03CRD. I want you to add your last name after CRD and then send this to me by email. You have until 11:59 p.m. on February 15th. So that should be a week from now. So I have a week to do this. It should not be super difficult. I don't expect it. But if you do run into issues, I guess the first thing I want you to do is post on GitHub issues, open a GitHub issue on our 2024 DSA GitHub repo, where if you have a problem, if you run into code issues, post there. I want first to give the chance of your classmates to help you. that counts towards participation. So both asking questions, but also answering questions, helping others on GitHub helps on your participation grade. And if it's been a while, maybe a day, and nobody helped you, I would come and jump in and help you. And if you need to connect via Zoom, we can do that. But I do want you all to perhaps start with Google, ChatGPT, Stack Overflow. If none of that works, post on our GitHub issues on our page. If that doesn't work, I'll jump in and try to help you as well. Okay, I think that's all I had. If you have any questions or issues, let me know. I'll stick around for another moment. And if not, I'll see you on Tuesday.